In this video, I want to go over how you obtain some output variable y, how you obtain the density for that variable in terms of knowledge of some input variable density x, as well as some mapping f of x, which is used to map x to y. So the question is, how do we obtain this output function and this output density? This monotonic, or this mapping function, is defined to be monotonic, meaning it's there's a one-to-one relation between the x and y values. We'll do an example shortly, and hopefully that will illustrate. So here I've given an example mapping function f of x that will be used to transform input terms x into our output terms y. I think this particular function is an arctangent function. So the key thing to know about this transformation is for every x value corresponds to exactly one y value. Okay, so we'll have one value of x, and it will map to some y in a one-to-one relationship as shown here. Notice you don't have some behavior of this function where a particular value of y may map to two values of x. You only have a single x and a single y. So that's what we refer to when we say monotonic. So anyway, the fundamental relationship at play in mapping densities is, I guess, more of a variation of common sense. Namely, if you've got some chance px of x times dx, that x has some value between x and x plus dx, then basically that is what will map to the y-axis. Namely, if let's grab some representative x value, say here. Integral of px dx over this small infinitesimal x interval will map to some spread in the y interval similarly. That's how the probabilities map across this transformation function. So what we'll see in shortly is that we can modify this relationship so that we get a single expression, a closed form expression for p of y in terms of p of x. And that's fundamentally what we're after, since with this we can calculate terms such as, the expected value of y, the variance of y, etc. All those can be calculated once we know y's density, the fundamental statistical characterization of y. So let's obtain what that form is. We'll begin by rewriting our main expression here relating the densities. And we say, since we know y is some function of x, we can basically say dy is df of x dx times dx, and we'll get an expression for this y term. More specifically, we may find the inverse mapping. F is some inverse function of y, this inverse mapping, and either obtain dy dx or dx dy. The point to make with this is we can use this transformation function between x and y and get either this term or this term. So once we have that, it's basically a game of moving this term to this side of the equation. And so we'll have p sub y of y is p sub x of x times dx dy. What I'm going to do here is put a absolute value sign, since this particular mapping between y and x may have negative values, and it doesn't make sense to speak of those in terms of a probability density. So all we need to know really is the magnitude of that transformation function's slope. And to repeat what I said earlier, we can have either this form, or we can also say p sub x of x all over magnitude dy dx. Whichever of these two forms is most analytically simple to express is what we'll choose. Another thing we'll need to do in forming this expression is to make sure all these x terms, I mean, in the end of the day, we want an expression in terms of y, output variable y. We don't want to have y as in terms of x. We want to have closed form function in terms of y. So what we'll also do is we'll take the x density, but instead of using the variable x inside of that expression, we'll do the inverse mapping between x and y and get us the x density in terms of the y variable. This probably will make more sense when we go through some examples, but I just wanted to make sure that this fundamental expression is obtained. So that's basically how we map inputs to outputs. And let me give a graphical example again with that arctangent function to kind of illustrate these concepts at play. So here we return to the example mapping function that we gave earlier, and I'm going to just show the goal here is just to qualitatively give an idea of what's going on with the expression p sub y of y is p sub x of inverse of y divided by, I'm going to say dy dx. I just moved that expression down here so that it's a little easier to read. So let's consider an example distribution p sub x of x and see qualitatively at least how that maps into y. Again, we basically expect, say for a uniformly distributed p of x, you basically expect p of y to reflect the magnitude of that derivative as mapped with when that uniform density maps into y. We'll see that shortly. Okay, I moved things around a little bit, but basically we see here in terms of input variable x a representative probability density. This is a uniform density function for, I think, in like 7 million runs or so, actually 1 million in MATLAB, and this is the histogram. But if you were to take this density and to map it through this function in MATLAB and look at the resulting output density, then the resulting distribution is as shown here. So we can kind of understand how this qualitatively makes sense. Specifically, let's look at value. This basically has some variety of slopes. Here we have a low slope. Here we have a high slope, and again another low slope area. So where you have a low slope, that's where this term here gets to be small. And so if the inverse is small, then this if this becomes low, then this becomes high, conversely. So we can see that, these regions in y where the slope is low, corresponding to a low slope in the transformation, that's where you have a large value of the density function. So that makes qualitative sense. Now, similarly, where you have a rather high slope area, we see a small value in the probability density of y. You can take this example and extend it a little bit. For example, the x values, as we've chosen them, I think I chose between minus pi and pi. If we instead did the density, say, starting here and here, or starting here and roughly here, you would expect, I think this arctangent, I think it approaches a asymptote at pi over 2. So you would expect to see an even larger density of y if the x values shifted over a bit more. So that's qualitatively how to understand what's going on between this density function mapping. So again, this is how we relate the density in y to some input density in x.